Okay, I think we're fine recording. So the first procedure that we do is one that computes the sum of squares of two numbers, right? Very simple. So the definition of a procedure is introduced by the keyword def. We pick a name for the procedure, for instance, sum of squares x, y, and then the body of the definition follows, and then we introduce the body with a colon. So already you see the indentation telling you that, yes, this is going to be the body. And we're going to return the value of x times x plus y times y. Okay? So this is all. We compute an expression, and then we'll see later that the body can be multiple statements. So the return statement tells what the value that is, what the result is. All right? You can think of this as a mathematical function. In mathematics, you'd have said fxy equals, right? You define fxy as being x squared plus y squared. So it's exactly the same as that. So typically, what we do once we have defined a procedure is to check how it works. So we're going to use it a few times. Print sum of squares of 3 and 4 is, and we're going to call here sum of squares 3 and 4. Let me close this so we have more screen space. Print sum of squares of 10 and 20 is sum of squares 10, 20. All right, so what we can do now, after saving, is to run this program. And we're going to see that the sum of squares of 3 and 4 is 25. Sum of squares of 10 and 20 is 500. Yeah, very simple. Okay? Why do we use procedures? Because they are a repeatable computation, right? So usually what you'll see is that the body of the procedure is very large, relatively large, right? And then in order to repeat that computation, you see this computation is invoked once here and then again here. The repetition doesn't cost us that much. It's just one extra line, right? We don't have to type again the entire body of the procedure to perform the same computation. Now, this is a very simple thing and it's just introductory, right? Let's try to compute something more interesting, right? So, for instance, let's try to compute the greatest common divisor of two numbers. All right? What's the greatest common divisor of two positive integers? For instance, if I have 100 and 44, what's the greatest common divisor? Nobody can tell me what the greatest common divisor is? Yes, the greatest number I can divide into two numbers. All right? So can anyone guess what it is here? Four, right? So 44 is 11 times 4. 100 is 25 times 4, right? So 4 is the largest thing that is in common. All right? How do we find out? Let's say we take let's say we take two more interesting numbers. Let's say I take 144 and 120. What would be the greatest common divisor? Right, it's 12. I'll tell you very quickly. Right, so we can compute this in two ways. Right, conceptually, the naive way, the conceptually simple way, is going to be by subtracting the numbers, whichever is the greater from whichever is the smaller from whichever is the greater, right? So I can do 144 minus 120, right? And that will leave me with 22 and 120. Sorry, 24 and 120. Right? And now 24 is smaller, so I'm going to do 120 minus 24, which is 96, right? So I'm going to be left with 96 and so 24 and 96. So again, 96 is bigger. 96 minus 24 is 72, right? So I'm going to be left with 24 and 72. And 72 minus 24 is, what is there, 48, right? Is it 48? Is the greatest divisor 24? Might be 24, yeah. So 72 minus 24 is going to be 48 and 24. 24, right? 48 minus 24 is 24. So I'm going to have 24 and 24. And at this point, because they're equal, I can conclude that 24 is the greatest common divisor, right? Or I can go one step further and be left with 24 and 0, because one of them is 0. I can determine that the other one is the greatest common divisor, right? So this is a very simple procedure. It's a very simple algorithm. The one that is a bit faster is to do the remainder, right? So 144 and 120. So 144 divided by 120, what's the remainder? And the remainder is 24. So I'm going to keep 24 and 120. Now I'm going to say 120 divided by 24, and the remainder is 0, right? The quotient is 5 and the remainder is 0. So I'm going to be left with 24 and 0. And as before, because one of them is 0, the other one is the greatest common divisor. This one works a lot faster. This one is called what? Whose algorithm? It's somebody's algorithm. Really? It's Euclid's algorithm, okay? All right. So Euclid's algorithm, let's try to implement that. So I'm going to say def greatest common divisor, and I'm going to take two numbers, a and b. They're both supposed to be integers, right? So the first trick we apply is if a is smaller than b, I'm going to return GCD of b and a. So I'm going to always want to assume that the first number is greater than the second. Okay? Now, if b is equal to 0, I want to return a. Right? If one of them is 0, the other one is the greatest common divisor. And then return GCD of, so a is always the greater one, right? But when I take the remainder of a divided by b, that remainder is less than b. So I want to always have the first number as being the bigger one. So I'm going to say b and a remainder modulo b. Okay? So this should give me the result. So what we were saying before is that the GCD of a and b, with a being greater than b, is the same as the GCD of b and a remainder b. They're the same. It's the same number, right? It's the same greatest common divisor. So fine. We can now test our procedure. So I'm going to print an empty line between the previous two lines. So just to show that we have gone to a new section of the code. So we're going to say print GCD tests. All right. Here we might be nice and say print sum of square tests. And let's do two tests. Print the GCD of, what do we have? So let's put them in reverse order and see that it still works. 120 and 144 is, and we're going to have GCD of 120 and 144. Print the GCD of, what other numbers might be interesting? So let's do an interesting experiment, right? The GCD of so let's define two numbers, x equals, and I'm going to say 2 times 2 times 3 times 5 times 5 times 7. So notice that all of these are prime numbers. 5 times 5 times 7 times 11, right? And y is equal to 2 times 5 times 13. No, does not have 2's. 5 times 3 times 5 times 13, right? So then what will be the greatest common divisor? All of them are prime numbers, right? So I have in common a 3 and a 5 here and a 3 and a 5 here, right? So the greatest common divisor should be 15. I don't even know what these values are, but I'm going to say the GCD of x and y is GCD of x and y. And we're going to find out what x and y are. We don't know what they are. And also what their GCD is. And we're expecting the GCD to be 15. So once we've done this, we're going to save. We're going to go here, run our program again, right? So we see that the GCD of 120 and 144 is 24, which is something we knew already. And then the more interesting one is the second one, where the GCD of 23,100 and 195 is 15, right? We sort of created these numbers in a way where we wouldn't know the final value, okay? But we knew for sure that the GCD would be 15 because they have in common the 3 and the 5, right? So 3 times 5 is 15. That would be the GCD. So this means that our code is correct. Okay, let's look a little bit at the execution of GCD. So notice that this is a procedure that refers to itself. So before the definition being completed, it invokes itself. And often beginners wonder whether this is a chicken and egg problem, right? How does this work, right? It works in a very simple fashion, and I'm going to showcase right here. So I'm going to create a little bit of space, and I'm going to print the sequence. So let's say that we have GCD of, what did we do? What did we use? We used this number. I would tell me the value, but I can get the value from here, right? So let's take this one, because this one is probably more interesting. So this one and 195, right? So let's see what's happening here. Okay, so we are invoking this. It goes inside. Is A less than B? No. Is B equal 0? No. So we're going to return GCD of B and A% B, right? So the next computation is GCD of B, which is 195, and 23,100 divided by 195. So we need to find out this value. And I'm going to show you how to find this value. If I go in Python without an argument, Python 3, I'm going to go into the interactive Python environment. Here, I can type expressions and see their value. We saw that last night, right? So I'm going to compute 23,100% 195, right? What's the value? It's 90. So the GCD of 23,100 and 195 is the same as the GCD of 195. So notice that this B is 195, and we put it here. So GCD, in the second invocation, GCD will have 195 as the first argument. The second argument is A% B, which is 23,100% 195, and we just saw that that result is 90. Yes? So in the next step, what's going to happen? Well, I'm going to compute again GCD of AB. Is A less than B? No. Is B equal to 0? No. So I'm going to return GCD of B and A% B. So GCD of, now B is 90, right? And the second argument is 195% 90. So I'm going to go here, 195% 90. And I get the result 15, right? I get the result 15 here. So this is my third invocation. In the third invocation, I'm going to compute GCD AB again. If is A less than B? No. Is B equal to 0? No. So I'm going to return GCD of B and A% B. So I'm going to have here GCD of 15 and 90% 15, which we know it's 0, right? Because 90 is 15 times 6. So now, this is the fourth invocation of GCD. So I'm going to go back here, right? Is A less than B? No. Is B equal to 0? Yes. Return A. The result of this is 15. So this is how this thing gets evaluated. Is this clear? So let me repeat that. We start with this, and we go through the body of the function. As we go through the body of the function, right, through the entire body in the first invocation, A is 23,100, B is 195, right? So 23,100 is not less than 195, right? So I can't go here. I will go to the next if. Is B equal to 0? Is 195 equal to 0? No. So I can't go here. I will move on to the next line, right? So I'm going to return GCD of B and A% B, right? So the B that I had here goes to be the first argument. And the second argument is the result of this expression. So 23,100 divided by 195 has a remainder of 90. This is what we put here, the remainder of that division. Okay? So this is the second invocation. We go to the top, and in the second invocation, A is 195, B is 90. Yes? Is A less than B? 195 is not less than 90. Is B equal to 0? 90 is not equal to 0. So we're going to have to go here. Yes? So we're going to go to the third invocation. In the third invocation, GCD, the first argument is B. So you see the 90 here, which used to be B, goes to the first position. And then for the second position, I will have A% B. So the result of dividing 195 by 90, the remainder of that is 15. Right? So this is what I put here. And we go to the third invocation. So Is A less than B? 90 is not less than 15. Is 15 equal to 0? No. So we're going to go to the fourth invocation, GCD of B%B, right? So the B here becomes the first argument, and A%B, right, is 90 divided by 15. Take the remainder of that, which is 0. So we go again through the procedure. Is A less than B? No, 15 is not less than 0. Is B equals 0? Is 0 equals to 0? Yes. So we're returning A. Whatever is on the first position, that's what we're returning. Whatever is on the first position, this is what we return here. This is the final value. Clear? So this is how the computer executes the program. Cool. Let's write another one that tells us whether a number is prime. When is a number prime? Yes, so the only divisors are 1 and itself, right? There's no other divisors. All right, so we are going to write a helper. We're going to learn how to write a helper. I'm going to write a helper first outside. All right, so the helper is going to return true, and we're going to learn a new type of value, which is booleans, right? Truth values, which are true or false. Okay, let's practice true or false, right? So this is true, has to be capitalized, and this is false. All right, and true and false is false, and true or false is true. Yes, not true is false, not false is true. 2 less than 3 is true, 2 greater than 3 is false. 2 less than 3 or 2 greater than 3 is true, right? 2 is either greater than 3 or less than. One of them for sure, right? So this essentially evaluates to true, this evaluates to false, and we're in this case where the first expression is true, the second expression is false, so the result is true. Yeah? Are we cool? Okay. So I'm going to define a helper which is going to be true if the number x has no divisors greater than y. Okay? So return. So the interesting thing is now that, you see, if x has no divisors less than the square root of x, x also will not have divisors greater than the square root of x. Does that make sense? So you see, if I take a number like 100, right? Square root is 10. 101. So the square root is around 10. 101 happens to be a prime, right? So let's take 100 first, right? So the square root is 10. For every divisor below 10, let's say 2, there is a divisor above 10, 50, right? So 2 times 50 makes 100. If I pick one that is lower than the square root, there necessarily has to be one that is greater than the square root. So if I tested all of them that are smaller than the square root, I don't need to go beyond the square root to test, right? So what I'm saying here is that this needs to be true, right? I wanted this to be true if x has no divisors greater than y. It might have divisors less than y, but it doesn't have divisors greater than y. So if y times y is greater than x, that means that y is greater than the square root of x, and this is true already, right? There's no divisors. All right, and sorry, this is possible, or there's one possibility. x% y not equal to 0. So if x% y not equal to 0, this is how we say not equal. x% y not equal to 0. Why is that, right? If x% y, x is the remainder of the division by y. If that is not 0, it means that y is not a divisor of x. And helper of x and y plus 1. Right? So helper is true, helper of x and y is true if x has no divisors greater than 1. So now, if for s prime I say return helper of x and 2, this means that x has no divisors greater or equal to 2, which means that x is actually prime. Right? So this is an interesting turn of events. We had to generalize. We had to come up with a helper that has an extra argument here in order to be able to come up with a solution. Now, this helper is not very useful outside of primes, right? It's a helper for primes, but outside of the context of primes is not very useful. So I'm going to put it inside. I can actually put it inside the definition of prime. You see, I can take this entire definition. It was outside. I can put it inside. I can indent it completely, and it becomes hidden inside. It's not visible outside of his prime, which is good. We don't want to add names indiscriminately. So now let's check whether our is prime function, the procedure is correct. So let's do another print for a empty line. Print prime test. All right. Print 12 is prime. So we expect false here, right? Print 13 is prime. Print 101 is prime. All right, save, and let's try. So this is the interactive prompt. We have to get out of it in order to run the program. So you can get out of it with exit, right? Another way to get out of it, if you're on a Mac, is to type Control-D. That doesn't work on Windows, unfortunately. So Python 3 procedures, and we see that 12 being prime is false, 13 being prime is true, 101 being prime is true, and you can try whatever numbers you like. Pardon?
Why do you exit?
Oh, I can't run the primes program from here. If I'm here, how do I run the primes program? I can't. There's no way. Actually, let me check. So if I do import procedures, okay, so that works. I can import it. I can say import procedures, and then it would run. It's not a standard way of doing things, though. But I mean, notice the fact that I can't go here and just say procedures. This will not work. Worse even, I can say Python 3 procedures. Yeah. Cool. So for the last one, let's do Fibonacci. Do you know the Fibonacci numbers? What's the definition of the Fibonacci numbers? Yeah, so it's a sequence where every number is we start at 1 and 1, or at 0 and 1 if you like, and every number is the sum of the previous two. Do you know where it comes from?
It occurs in nature, right? Some ratio. Golden ratio.
Yeah, so it recurs in nature. The golden ratio, so it turns out that the value of the Fibonacci number, Fn, is 1 plus SQRT5 divided by 2, all this to the power of n. And the proof of this is very, very beautiful. You can search it in Wikipedia. 1 minus SQRT5 divided by 2 to the power of n. So it looks like this is an irrational number, but believe it or not, it's always an integer. All right. And the interesting thing is that this number is smaller than 1. So as you raise it to the power of n, a number below 1, as you raise the power of n, goes very close to 0, right? Closer and closer to 0. So this dominates. All right. And if you take the closest integer to this, right, actually you get the Fibonacci, because this number is very close to 0, right? So from n equals to 10 or so, right, it's essentially the integer part of the highlighted part, right? So this number is called the golden ratio. Anyway, it's been observed to appear, but it has a very interesting origin, right? In the Middle Ages, actually earlier than the Middle Ages, in the 1100s, Italian farmers were wondering, if you start with a pair of rabbits, all right, how many rabbits do you end up? And let's say the mating cycle is 1 month, right? Meaning that after 1 month, the rabbits mature, right? They can mate, and after another month, the female gives birth, right? And then immediately they can mate and then gives birth again, right? So how many rabbits would you end up after n months, right? And it turns out that it's the Fibonacci. Number, right? If you look at two numbers in the series, this is the number that you have currently, but the previous one is the number of adult rabbits that can mate. The rest of them, the difference between two is immature rabbits that cannot mate yet, right? So those are mating, and you're going to add that number because each of them is going to spawn, and you can add that number to the current number, right? So this series represents the number of rabbits that you would have after n months, right? This was a very serious problem in the 1100s. People wanted to predict how many rabbits they would have after a while. It's a phenomenon that was is seen in many cases in nature, right? Because it's a very natural phenomenon. So in a lot of cases, once offsprings are spawned, they need to mature before they can have their own offsprings, right? So because of that, Fibonacci sequence plays a very important role. Cool. So let's define a procedure that tells us what's the Fibonacci number of n. So fib n. This is a very simple definition. So if n is less than 2, so either 0 or 1, return n. So if n is 0, return 0. If n is 1, return 1. The sequence can start from 0 and 1 if we so want. Else, and I'm going to show an else, even though it's not necessary because I've used a return, but it's good practice to have an else, to use the else clause. So we're going to return Fibonacci of n minus 1 plus Fibonacci of n minus 2. So because I'm in Python, I also have to use a return statement. Okay? So let's print another empty line, print all right, so print and let's print all of them till maybe we print about 10 of them. So 1, 2, 3. There's better ways of doing this, but let's not jump the gun. So we have 11 numbers. And these are the numbers, right? Clear? So next time we're going to continue with defining procedures and exploring computations via procedures. We're going to see how we can solve equations that you wouldn't be able to solve analytically. All right. After that, we're going to start exploring aggregated structures such as lists, tuples, dictionaries, and so on. And then we're going to go into building a game. Questions? All good? Cool. See you next time. I will upload the recording. I will upload the code.